Welcome to this lecture on finite automata with output. Now, finite automata that we've done before does have output. The output is a yes or a no. Yes, this word is accepted by the finite automata, or no, it isn't. But now we're going to make finite automatas a little bit more useful in that they can provide more output. So finite automata with an output has an input language, and in this case, A and B's, and an output alphabet that has zeros and ones. So an input alphabet, not an input language, and an output alphabet. Now, in this case, we also don't care whether or not the finite automata accepts the word or doesn't accept the word. It's just going to take in an input word and produce an output. And this machine is called a Moore machine. We're also going to study Mealy machines, and we'll learn the difference between the two of them. Now, Moore is the last name of the person who created this machine. And so the very first step we do is we have our input word, which is this word down here. And we start in this state. See, the arrow points to the start state. That's because we fill up the inside of this state with the output. These are just labeling the states. We don't really need them. We could just put the output, which is the 0, 0, 0, and 1, which is the output. So let's go ahead and try running this word on this word right here on this Moore machine. So we start in this state and automatically, no matter what, we produce a letter of output, which is a 0. The reason why we produce 0 is because we got 0 inside of that state. Now this is one character of output that doesn't match anything in our input. And that's one way that you can remember that it's a Moore machine because it produces one more letter. The very first state produces a letter, and there's no letters that we've read to produce it. Next, we read an A, and in this state, when we read an A, we go to this state and we produce an output of 0. Then another A that causes us to go to this state, which produces another output of 0. Finally, another A that produces another 0. And then a B causes us to move to this state to produce an output of 1. Next, we read an A, which causes us to move to this state and produce an output of 0. Then a B, which causes us to move to this state and produce a 0. Followed by another B, which causes us to do that and produce a 0. Then we get an A, which moves us to that state and produces a 0. Another A, which moves us to that state and produces a 0. Then finally a B, which causes us to move to this state that produces a 1. And then another B, which causes us to move back to that state and produces a 0. So our input word is this, made up of A and B's, and this is our output word. And once again, it has one more letter than the input, or one more character than the input word, because we automatically land in a start state that produces an output. Now, this Moore machine was actually designed to count the number of substrings of A, B. Every time we get an A, B, we land in this state and produce a 1, so we can count the number of 1s that we have. We see that there's 2 of them. That means inside of this string right here, A, B appears twice, once right here, and once again right here. Now let's look at Mealy machines. And Mealy is the last name of the person that created these machines. Instead of putting the input or the output that we produce inside of this state, we put the output along the edges. So if I'm in this state and I read an A, then I move to that state and produce a 0. So let's run this Mealy machine on this input word. So if we're in the start state, now the start state is indicated by the arrow, and we're reading an A, we move to this state and produce a 0 for output. Now if we're in this state and we read an A, we move to that state and produce a 1 for output. Now if we're in this state and we read an A, we go to this state, back to this state, and produce a 1 for output. If we're in this state right here, and we read a B, we go back to that state and produce a 1 for our output. And if we're in this state and we read a B, we go to this state and produce a 0 for output. So if this is the input word, then this becomes the output word. Okay, now we're going to prove that every Moore machine can be converted into a Mealy machine that produces the same output, except for that beginning extra character that every output is going to have, because a Moore machine produces one extra character and a Mealy machine doesn't. But other than that, the output that a Moore machine produces on a word will be equal to the output that the Mealy machine produces. So up here, I have a Moore machine because the output is inside of the states, and I'm going to convert that to a Mealy machine. So all we have to do is copy the states. So I've copied all of these states and I made new states, but I've omitted the output in these states because in a Mealy machine, you don't have an output. We'll go ahead and mark the start state, and then we could see if we're in this state and we read an A, we go to this state and produce a 1 for the output. So we're going to take the output and push it out to the edges. Notice the edges that come in, we're going to grab the output and push it onto that edge. So in this case, when we read an A, we're going to get an output of a 1. Now if we look at this state, it has 3 edges coming into it, 1, 2, 3, and it always produces an output. So for the 3 edges that come into that state, we're going to push the output of 1 out onto the edges. Okay, so we can see that this 1 output got pushed out onto all the edges that go into that one. Now in this state, we have 1, 2, 3 outputs as well, or 3 edges coming in, so this 0 needs to be pushed out to those 3 edges. And now we're done. The only thing is the Moore machine will produce an extra 0 at the beginning that will not get produced, but as you follow this, if we got an A, we produce a 1. If we get an A, we produce a 1 along that edge. So now we can convert all Moore machines to Mealy machines. Now let's go the opposite way. Let's convert Mealy machines into Moore machines. Now you might think that going from a Mealy to a Moore machine is just as easy, but it actually gets a little more complicated. And that is because, say, look at this case right here. Basically, we're going to take the output and push it into the state. But in this case, we take a 1 and push it into this state, and we'd also take a 0 and push it into that state. And this state cannot produce 2 different outputs. So what we really need to do is copy this state down 2 times, one that produces an output of 1 and another that produces an output of 0. And we'll go ahead and copy the start state as well. And when the start state, when we get an A, we go to this state and we produce a 1. So we want that to go to the Q2 state when we get an A to produce a 1. Now let's look at the other edges that come in here. We have an edge coming in here, an edge coming in here when we read a B. So let's work on this one right here. When we're in state Q2 and we want to go back to state Q2 and we produce a 0. So when we get a B, we just go there, but in also this state, we also go here because whenever we get a B, we want to go to the Q2 state that produces a 0. Now, when we get an A in Q2, we're going to go up to that state. Now, this state's a little nicer because both edges coming into it have a 1, so we only need one of those states. But we also have to remember there's two Q2 states, and we need an A exit on both of them, so we got to draw in this edge as well. Now let's focus on this state. We have a 0 coming in, and there's only one edge coming in on this one, so that's nice. We don't have to copy it down twice. So let's go ahead and create that state. And notice when B0 comes in, it wants to produce a 0. So let's go ahead and put that down. Now let's go ahead and work on the edges coming out. If you notice, when we come out, we want to produce a 0 and go to Q2. So we have to go to the Q2 0 state. Okay. Now when we come out this way, we want to go to the Q0 state that produces a 1. So we'll just go ahead and mark this as a 1 and put that there and put B. The only problem is this state also has an edge coming into it that produces a 0, so we're going to need a Q00 state. In this case, when we get an A, we go there. Now we got to be careful because now we have two copies of this state, and they both need A and B exits. We already have the A and B exits for the one out the state that produces a 1, but we don't have A and B exits. They're going to go to the same place. We just need to copy them in. So when we get an A here, we want to go there. And when we get a B in this state, we want to go there. Now that we have all of the edges and every state has an A and B exit in it because a finite automata needs that, we next need to decide what is going to be our start state, because now we have the old start state has two copies of itself. And because a Moore machine produces one extra character at the beginning of the word, it's up to you to decide. Do you want that extra character to be a 0 or a 1? If you want it to be a 1, choose that as your start state. If you want it to be a 0, choose that as your start state. We'll just go ahead and choose 0 for this case. But of course, you could choose 1 as well, and they'd both be correct. Unless your output means something and you can only have a certain number of 1s in it or a certain number of 0s, then you might want to choose the other one. But in most cases, you can just choose either one as your start state. And now we've been able to convert a Mealy machine into a Moore machine. So that means these two machines are equal in power. Any input, any machine you build using the Moore machine, you can convert it into a Mealy machine and have it do basically the same thing. The only difference being that a Moore machine will always have one extra character at the beginning. But since every word has the same extra character, that extra character really doesn't mean anything. So thanks for watching.